He actually received his PhD, I guess, more or less around the time when I was born. So he did that in London, at UC London, and it was actually rocket flights before satellites were invented to do X-ray astronomy. And I think one of the first projects was to look at the X-ray background and look for fluctuations therein. And rockets were launched, of course, not from England, but from Australia and Sardinia. That were the two places. And moving on from there, actually, Andy wanted to go to the US, but in the end he didn't, because he didn't get a visa. And that forced him to stay actually in the UK, where he soon then settled to go to Cambridge, where, how did you put it, where Martin Rees was the attraction to be with. And that's then where he stayed on forever. So Andy's, of course, famous for a lot of work which he has been doing, and maybe the one which is most connected, at least to what I'm doing, is the iron lines, which you can see in the reflected light of accreting sources. So it's one way where we can hope to measure spins of black holes. So that's of course where Andy's work is seminal. And the other big pillar of his work is actually galaxy clusters, and that's what he'll be talking about today. He also was an editor, for example, of the monthly notices for 29 years, if I'm not mistaken, was president of the Royal Astronomical Society, was the director of the Institute for Astronomy in Cambridge, and currently enjoys an ERC Advanced grant. So I think that's not the worst thing to have, because Andy actually is Professor Emeritus by now. Andy, I think enough said. The stage, the screen is all yours. I'm looking forward to your talk.
Thank you, Stefan. Let's hope this works. Okay, and I'm just going to make sure the arrow doesn't disappear. So I'm just going to do this. Yeah, only Perfect. Just like that. So I'm going to talk about, can you hear me okay? Just to check.
Yes, everything is fine. Yes.
Excellent, good. So I'm going to talk about hidden cooling flows in clusters of galaxies. So cooling flows is a topic that I started working on 45 years ago, a long time ago, and that I'm now going back to it. I go back to it and think about it a lot. Jeremy Sanders has helped me with this work by providing the data, and so I don't blame him if you dislike the plots and results I obtain, but there we are. So let's go away from this starting picture, which is showing the center of the Centaurus cluster, the galaxy NGC 4696, which is part of a beautiful representation of some HST data. Now, in case there are any students who don't know what clusters of galaxies are, I just give a preliminary here that they've got total masses of 10 to the 14, 10 to the 15 solar masses. They're still forming now. They're the largest bound structures in the universe, and they consist mostly of dark matter and 16% baryons, most of which is in the form of the hot gas, the intracluster medium, and the hot gas has much more mass than all the stars in the galaxies in the cluster. The temperature of that gas is close to the virial temperature of the region. It's at 10 to the 7 to 10 to the 8 K, or can be a bit hotter. And that's roughly 1 to 10 keV, because I'll go interchangeably between 10 to the 7 K, I call 1 keV. It's not exactly, but let's do that. And the X-ray luminosity is it's mainly due to Bremsstrahlung, it goes from 5 times 10 to the 43 to maybe 5 times 10 to the 45 ergs per second. So they can be very luminous and compete with quasars. And I'm sure that the E Rosita sky is littered with clusters of galaxies, and I know you're finding many new ones. So here is a cluster. This is the brightest cluster in the sky. It's the Perseus cluster, and you can see it with an underlying optical image. And from the X-ray emission, you can get the gas density and temperature, assuming it's Bremsstrahlung emission. And so we can learn much about it. And there are two classes of clusters out there. One is the cool core cluster, the other non-cool core, which is like the Coma cluster, and the Perseus cluster is a cool core. That means as you go from the outside of the cluster inwards, so what is happening is you go from being at the virial temperature of the cluster down to a factor of 2 or 3 in temperature or more. That's part of what the talk is all about. But essentially, to support the weight of the overlying gas, as the temperature drops into the center, the density goes up, and the emission is proportional to the density squared. So the surface brightness goes up enormously in the center, and they've got very sharp cores. And we're talking here in this talk about essentially what's going on in cool core clusters. This is 2 megaparsecs on this representation made by Steve Allen. And this is like the inner 100 kiloparsecs. It's the top of this spike. And if we look at it in terms of the temperature profile to some visual radius, then the temperature in this inner part, the inner 100 kiloparsecs or so, drops away by a factor of 2 or 3 in this kind of plot. And what is also happening as you go from here down to here, if we compare the thermal content of the gas, 3 halves nkt, with the rate at which it's cooling, it's radiating energy in terms of Bremsstrahlung. Compare the two, you get a cooling time, and that cooling time drops from the age of the universe and above down as you go in towards the centers of these clusters. It drops down to essentially less than a gigayear and can go down to less than 10 to the 8 years. And so that's, I'm just going to try, yes, that's better. I've just got a little box on the side. That's what's happening. And so the fact that as we go into the center, the cooling time gets less and less, that suggests that something might be going on here. And basically, what we want to know is the gas cooling all the way down, in which case we have a cooling flow. And when XMM was launched about 22 years ago, then people used the XMM reflection grating spectrometer to make spectra at relatively high resolution for X-rays in the center, and it could see emission lines and so forth. And what was actually observed, and this is an example of one cool core cluster in work by Jelle de Pla, that basically that the spectrum dies like this, and we expect if there is cooling going on all the way down, you'd expect to see this red line, these emission lines. This is oxygen 8. These are the iron 17 lines, and then this is a mess of iron 21 through iron 24, the iron L complex here. And what you can see is much of it is missing. You could see some of it. That's the lines associated with higher temperature gas. But once you get down below a keV, below 10 to the 7 K, that gas emission is missing. So it looks as though at the centers of the clusters, the temperature goes down to a half to 1/3 of the outer temperature. And this, as I say, was completely clear about 22 years ago from XMM data. It was also emerging from Chandra data, but we'd also found evidence for something going wrong with a steady cooling flow in ROSAT data and ASCA data. So this is the Perseus cluster showing us a beautiful Chandra image. I was the PI of many of the Chandra observations. I was lucky to get involved like that. And we've got this superb image which has over 100,000 photons in it, 100 million photons in. So it's got lots of resolution and so forth. And what we see at the center is a lot of structure. There is a nucleus, a bright nucleus in there. This blue stuff, the blue stuff is absorption of an intervening galaxy that lies between us and the Perseus cluster. We think it's near the edge of the Perseus cluster. We know it's far out in the cluster because if you look at the dark patches here, they go so dark, so deep, they essentially go down to 0 counts. that it must be on the outside of the cluster, otherwise intervening emission would have infilled it. So we can totally ignore that and look at this, what's there in the center. There are these bubbles above and below the central nucleus, and those bubbles are inflated by jets from the central black hole, and they are made of cosmic ray plasma and magnetic fields, and then they are buoyant in the intracluster plasma, and they rise up, making outer bubbles here and here. And this bubbles looks like it's been trashed a bit, and there's a story behind that which I won't go into. We can also see this feature here, which is the weak shock caused by the inflation of the bubbles, and that actually weak shock goes all the way round here like that. And then we've got filaments of gas, which we can see clearly in H-alpha emission in the optical band, but I don't want to go further into that. And this is what we can see, and it was pretty clear from the presence of these cavities that something is going on. A lot of energy has been injected by the central AGN, and that is bubbling at the center of the cluster, is then affecting all the rest of the gas. And maybe that's the explanation for why the gas is not seen much below a keV. Just as an aside, I want to show you some pictures taken earlier of the center of the Perseus cluster. This is the Einstein telescope image from 1980. This is ROSAT in 1992 in an HRI image that was led by Hans Boehringer. This is Chandra data from 2000 from one of my starting images. And you can see very clearly the bubbles are present, the inner bubbles are present in Chandra and ROSAT, but you don't see them at all in the Einstein image. And the reason for that is because the nucleus was much brighter then. You can see signs of this outer bubble here, but you can't see the central ones. And this is what the PSF of Einstein was. That's a point source, 3C273, a quasar. And it was so bright, of course, that the nucleus of Perseus was shining so brightly that it was smearing out what we can see. It was just the contrast. It wasn't sufficient contrast to see the bubbles. And I just want to connect that with what was found later. This is in black is the 90 gigahertz radio emission from the nucleus, and you can see it's highly variable. And when Einstein looked at it, it was around its brightest. And then when ROSAT looked at it, it was almost an order of magnitude fainter. And then when we looked at it with Chandra, it was down by another factor of 2 or 3. So it's interesting to think, I'll just go back here, that imagine that the brightness of the nucleus had been the same as it was when Chandra looked at it, then we would have seen an image very much like that one. And it's likely that the whole history of this subject would have been very different. And just in terms of the wonderful work that Stefan and Reinhard have been doing, it just makes me think that imagine the galactic center had been much brighter over the last few decades, as it has been maybe 100 years ago, 300 years ago. It was 1,000,000 times brighter, how history might have been a lot different. So let's move on to it. This is the radio emission. The radio plasma fills these inner bubbles, showing you what's going on. And then it's pushing the gas out, and then there's a weak shock on the outside running all the way around. And Eugene Chirazov has done lovely work theoretically on all of this and shown us how to take the bubbles and work out what the bubbling power is. By taking a bubble, you've got the volume of the cavity, you know what the pressure is from the surrounding gas, which you can measure from the density and temperature measured from X-rays. So you know what the pressure is inside as well. And so you've got the total energy in the bubble. And also you can look at the buoyancy time, how long before it's going to start floating upwards. And that's a few times the sound crossing time. And when you then convert that to a rate, you've got the power in the cavities. Some people call them cavities, not bubbles, but let's not argue about that. You get, that's the power in the cavity. This is the luminosity in the surrounding gas, less than the, we can call it a cooling radius, so out to 50 kiloparsecs, say, the total luminosity. And there seems to be some agreement, so it's quite possible that all this bubbling process is stopping the gas cooling any further. And that, you could say, is jolly good agreement for an astronomy plot, but if you look in detail, you might worry a little bit about saying it's got complete balance. But it looks as though much of the cooling in the core can be balanced by heating via the bubbles. And these are just a few other bubble, you can see bubbles in this object RBS 797, Abel 2052, and so on. And there's a review of all this kind of work by myself in Annual Reviews and McNamara and Nelson in 2012. But the question I want to deal with is actually cooling taking place in terms of, is cooling happening at temperatures below 10 million degrees, below 1 kV? Jeremy's made these nice plots here from Chandra X-ray imaging, where we can look at the temperature of the gas in the cluster, it comes down. We can look at the total gas mass, and it's going up like this. And we can look at the cooling time, that is dropping down in the Perseus cluster like that. And if you take the gas mass and divide it by the cooling time, that gives you a rough, very rough estimate of what you would get if there was a cooling flow. It's within a factor of 2, should we say. And you can see that if it were, then the cooling flow may be of the order of a couple of hundred solar masses per year. And what we find by doing spectral fitting like that is you get about 1/10 of that, or even less than that. So something is, it's being snuffed out at the center, if you like. And this plot here is from my student Hyun Liu's work, where he's looked at a whole bunch of clusters with the XMM RGS. He's fitted them with models involving a cooling flow and a CIE component, just a constant temperature component, and compared the two. These are upper limits, the pink ones, and these are measurements in the blue, but basically comparing the mass cooling rate with the mass cooling rate from a simple argument such as I've just given, then the ratio is such that it looks like most of them show less than 10% of what you would expect if the cooling was happening, was allowed to rip and there's nothing stopping it. So it looks like AGN feedback perhaps is really stopping cooling in cool core clusters. However, if you look at the relative cooling time carefully, and this was the work done by Elettra Panagiulio with me when she was a student here, and you see that the cooling time in many of these clusters drops down continuously, and it looks as though it just continues all the way to the center. We don't actually see different states of it. It looks, they all look sort of remarkably similar, and it looks as though everything is going to be very continuous. But when we actually try and measure, and Jeremy did this with Centaurus data with the RGS, look at the mass cooling rate below 1 kV, that mass cooling rate just drops off from around 10 solar masses per year down to below 1 solar mass per year as we go to the innermost cooler regions. So something is going on. It looks like AGN feedback in clusters and groups appears continuous and gentle, but the reduction of m dot at small radii and below 1 kV, it seems to me as though there's some sort of fine tuning, which I don't understand. Basically, it looks as though everything is shutting off as you get down to the lowest temperatures, when there's the least amount of energy to be released. When the cooling time is the shortest, then it all seems to shut off. And yet we don't see examples of things where there's, say, an excess of energy down there. They all look to be very similar. Always, and it doesn't look as though there's a large time dependence to it or anything like that. So something is going on. And one possibility which has been thought about, and this is not, I'm not the first time to say it, but maybe this complete decline in m dot can be explained by absorption. After all, the gas is cooling down, you're going to make lots of cold gas, then how about if the cold gas gets messed up and incorporated in the cooling gas? Then you're going to end up with photoelectric absorption acting on the softest gas, because photoelectric absorption, the cross sections go as e to the -3. So the cross sections are largest at lowest energies, and that's where the emission is coming out, and where the emission is lacking, it's at the lowest energies. I wrote a review with John Peterson, who worked a lot on the RGS data at the start of XMM in 2006, and we had this sentence in, and that is, absorption has generally been abandoned as an explanation, although no detailed test has been made of a model in which the absorption is intimately linked with the cooling gas clouds. So whilst absorption had been tried out in various observations, it had generally just been a sheet of absorption or something very simple. It hadn't actually gone and done something where the absorption and emission were sort of intimately linked. Let's see about cool gas. Is there a lot of cool gas in these objects? Yes, there is. This is a lovely picture of the core of the Perseus cluster that was made by Jay Gabony, who's essentially an amateur astronomer with a 20-inch telescope. And here you can see giant elliptical galaxies. And this is the central galaxy, NGC 1275, the center of this cool core. And you can see there's a lot of H-alpha emission. And you can also see in blue, there's star formation as well. So something is going on here. And this is the H-alpha filaments that have been known since the 1950s. And lots of nice images over the years, but I was lucky to get the HST images, and you can see this spectacular H-alpha nebula. And just to give you some scale, from down here to up to here is about 40 kiloparsecs, and going all the way up the top of this filament, which is going up a long way, it's around 80 kiloparsecs across. So it's a beautiful H-alpha and N2 nebula. When you look at the emission lines from that nebula, it's curious that the optical spectrum is unlike anything in our galaxy, other than the crab, actually. And with Gary Furland, we modeled this over 10 years ago and concluded it's probably due to energetic particles, which do the excitation. It could even be the hot gas, or it's absorbed X-rays. Some more recent work by Poles here. And also the sort of age that we deduce for things, these kind of filaments, is of the order of a gigayear, and they're growing in mass. And by the way, the weak shock actually runs along here. So there's something going on here, which I'll get back to later. Then a few years, well, some time back, Philippe Salome looked at it with IRAM. It was known from earlier work that there was strong CO from the center, but Philippe's work showed that the CO was detected all the way out along these filaments. Wherever you see H-alpha emission, then you also find CO emission. And the total mass of cold gas is somewhere between 2 and 5 times 10 to the 10 solar masses. So there's a lot of cold gas in this object. And also, this is an image from Jeremy Sanders. If you look at the X-ray image and compare it with an H-alpha image, you can see that there are bright patches of soft X-rays coincident with the H-alpha filaments. So the idea that the soft X-rays, the low energy X-rays, are also coming from a region which has got cold gas appears to be pretty good. There is some star formation, but it doesn't coincide with coal gas. This is a sort of extragalactic star formation occurring in the middle of the Perseus cluster, or it's at the edge of this whole filamentary nebula. There's a filament here, but the star formation is distinctly separate from it. Maybe this used to be a filament here, but it's actually decided to form stars. And this one is not forming stars. And if you study this, you can see it's composed of lots of star clusters, but they appear to be sort of falling. And I think it looks rather like a sort of experiment I witnessed when I was at school, where some potassium permanganate crystals were dropped into water, and you sort of see them drop down and with diffusion out the back. And anyway, it's what it looks like. And now I want to jump to the Centaurus cluster, which is closer than the Perseus cluster. It's a less massive cluster, less luminous, but still one of the sort of top 10 clusters in the sky, in the X-ray sky, that is. And this is an edge detection image that Jeremy's made, where you can see the center here. It's got all sorts of filaments and so forth. And this is what it looks like if you look at it in a red, green, blue, which is colored by the soft X-rays are red, and so on to the harder X-rays in the Chandra image. I think this is about a 3/4 of a megasecond image. It looks to me like something from, you know, this could be a body, and these are the sort of lung, this is a lung cavity or something, or maybe it's something you find on, if you go and look in a rock pool, you might see something looking like this. But we don't think it's alive, and it's got a nucleus here, and it's got radio lobes either side here. We can see those here. That's the nucleus. The JAC goes first of all north-south, then turns east-west. And you can possibly just see the extension of the radio down to the south there. This is our HST H-alpha image, and you can see lots of interesting filamentation there. And this is the soft X-rays. These are all to the same scale. They can go on top of each other. And this is the publicity image made by NASA and ESA for our HST data. And I think they've made a jolly nice job of it. And you can see not only is there lots of H-alpha emitting gas, but there's also a lot of dust. And these dust lanes have been known since the 1960s. There's a paper by Shobrook from 1966 or something. And you can see a lot of detailed emission there. And the nucleus is this thing here, which if you look, I'm not going to show you a detailed picture, has a sort of S shape on top of there. So I'm now going to talk about, go back to the topic of my talk. This is hidden cooling flows. The idea is that soft X-ray emitting gas is from the same regions as coal gas, and much of the cooling gas is embedded. That's what I mean by hidden. We need to reconsider absorption by coal gas. As I said, it's already been thought about in the past, and we thought it was the answer to ROSAT data back in 1997. Stephen Allen and I worked on it then. And the cooling power from below 1 kV is actually ultimately emitted by dust and gas in the far infrared and UV part of the spectrum. This is what where we get the model spectrum from, by thinking about gas, which is blue is going to be the absorber, pink is going to be the cooling flow emission, and we alternate absorber, cooling flow, etc. And of course, there can be absorption from our own galaxy. If you have something like that, then this emission is absorbed once, this one's absorbed twice, and so on. And if you add the emission up, it's right, it becomes a geometric series. And if you make the number of layers very large, you end up being able to approximate it like this, that the final flux that you detect is related to the total emission, and that's the total column density. And sigma, of course, is the cross-section, the photoelectric cross-section at that particular energy. And so we've used that on ROSA data. Steve Allen showed it worked very well with ASCA data. And my student, Helen Liu, has worked with XMM data. I have dug around and seen who else has thought about this and so forth. I found a paper by Norbert Werner from 2013. He looked at some filaments in Virgo and used the same model. And Stephen Walker has looked at the spectra, and I was involved in this, looked at the spectra of some of these filaments. And whilst he didn't use this model, he found evidence that there could be absorption. Now, if I take this absorption model and just apply it to a cooling flow, that's MKC flow is the name in XSpec of what the cooling flow model is. And this is now in UF-nu plotted against lambda of the spectrum. Then what we see is as you wind the column up from being very low, that's the top black one, down up to 3 times 10 to the 22, then everything drops down by well over an order of magnitude. And if we went further, it comes down. But whereas if you just put a simple sheet across, it would actually be sort of crashing like this. This allows there to be some emission from the outer parts, which have got very low amounts of absorption, and you get a much gentler kind of absorption effect. It's happening across the spectrum rather than just at one particular part of the spectrum. And what I've done is to apply it to data, the RGS data from Centaurus and Perseus, and just point out a couple of things with the spectra. I'm not going to dwell on this. This one is plotted in a linear fashion, and you can see this does have iron 17 lines, but the XMM RGS, of which there are 2, there's RGS 1 and 2, and they've each lost 1 chip. So there's gaps in the spectrum, and it depends upon how you plot it as to whether it's obvious. And there's another plot there, which is in log space, because I wanted to show what the components were better, and you can compare the 2. But let's not dwell on the spectra. What we can do is fit the amount of cooling flow there might be as a function of the column density. That's the total column in this multi-layer model. And I find that there's an acceptable region which is centered around 15, an M dot of 15 solar masses per year, and an absorption column just over 10 to the 22 square centimeter. When I go to Perseus and do the same, it seems to be, it's consistent with 0 or very low M dot, but it seems to like something around 80, and the column density is higher at somewhere between 5 and 10 times 10 to the 22. How does it come out? That energy that's been absorbed must be coming out somewhere. And the Herschel observations that we had of the Centaurus cluster analyzed by Rupal Mittal is shown here. And you can see this large bump here at 10 to the 12 Hertz, which of course is the around 100 microns, and this is where that emission is coming out. With Perseus, you can even image it, and it looks like this. And there's cold dust and warm dust. And remember, there's a very powerful nucleus in the middle of the Perseus cluster. We've also looked, I've also looked at Able 1835, which is at a redshift of 0.25, which is more than a factor of 10 further away than the Perseus cluster. This is what it looks like in X-rays. You can see it's got bubbles there and there. This is from work by Brian McNamara, and this is the CO image. It's got a very large mass of CO. This is HST far UV emission. There's star formation in this object of around 100 solar masses per year. If I go and do similarly with what I talked about with Perseus, then the m dot here can be many hundreds of solar masses per year, is what you might imagine. And the results that are coming out are, this is unabsorbed, this is absorbed m dot, and this is, I've also got an unabsorbed component, and the unabsorbed component is 300, and the absorbed component can be quite a lot more, and you have to add the two together. This is what Able 1835 looks like in Spitzer, and this was published by Igami in 2006. This is the spectrum down in the sub-millimeter, and it's got a large bump. And it's being compared with ARP 220 there, which is the dotted line. And there's, of course, this powerful radio AGN there, and the giant elliptical. That's a thought of what goes on at these short wavelengths. If we look at the numbers then, it turns out that take the far infrared luminosities, which are there, I can convert them to equivalent mass cooling rate of gas from 10 to the 7 K, and I get 11 for Centaurus and 2,000 and 10,000 for Able 1835. We're talking about hidden cooling rates of 15, 80, and 300. Now, they're well below these rates, thankfully, that you don't want them to be above, but this is saying this hidden cooling rate could also be hidden within the far infrared, because I don't know how to separate out the effect of the star formation or the nucleus of the object. These are dust masses and CO masses and star formation rates. So it's possible that hidden cooling flows where absorption's been included may lead to significant amounts of gas cooling in clusters, more cold gas being accumulated at rates of 10s to 100 solar masses per year or so. And if you let it go for a gigayear or so, you're talking about 10 to the 10 to 10 to the 11 solar masses of cold gas. Now, there is that kind of gas mass in these objects, but also we've got to think, is it going to be, even if we allow it to have even larger values, is it going to be too much? I stress there's a lot of cold gas observed in many cool cores, and I would like to speculate, just to think about this, perhaps there's more in the form of ultra cold clouds at less than 5K. Now, bubbles shocks also are going to destroy clouds and drag gas outwards, and that will also help to regulate the total central cool gas mass. And so I want to now spend just a few minutes looking at following these consequences and this speculation. The first thing is, if we look at Centaurus, and this is now looking at MUSE data that's been analyzed by Stephen Hamer, then here are the filaments in Centaurus. That's in nitrogen 2, and that's in H alpha. And this certainly seems fuzzier. Now, the nitrogen 2 emission line, this one, is much stronger than the H alpha here, a factor of several times stronger. So this is brighter than that, but it looks like this is somewhat more diffuse than this is. And it's intriguing to look also as you go north from this bright patch here, that's this patch here in this expanded version below. So we're now looking up here, that as you go up, Stephen found that in each of these anguli, you can still see the nitrogen 2 emission. And all the way up to this 6th one here, he's still seeing evidence that looks like there's some excess emission in the nitrogen 2. This, by the way, the gray is doing plus or minus 1 sigma. So it looks like it peters out somewhere in this bin. This is the 5th bin here, and it's quite clear there's something going on. So it looks as though there's weak emission extending beyond the filaments. There isn't just the filament emission, but there's some diffuse emission. And following this up is something we're trying to do. There are also strong abundance gradients at the centers of clusters. And this is NGC 4696, which has perhaps the most extreme abundance gradient. That's the one in the middle of the Centaurus cluster. If you measure the abundance from the X-ray spectra, Chandra spectra, then you'll find it's around 0.4 in the center, and it rises up to being 2, around 20 kiloparsecs. That's in iron. If you go to silicon, it's even higher. So there's this very steep abundance gradient. And I'm not going to go into the details of Electra's paper from 2012, where we discuss how you're going to get dust deposited from old stars, late type stars in the center of the cool core. And maybe it gets mixed up with the cold gas and gets dragged outwards by the bubbling phenomenon. So probably this clouds of cold gas are being dragged outwards, and then they mix in out here where the abundance is highest. But there's something funny about the abundances here. And all of this was reanalyzed by Luxuria in 2019 and essentially agree with the key things that we had found. So the gas is in some sort of cycle of being pulled out from the center as well. Gary Furland is a visitor here at the Institute, and I've been quizzing him on how cold can clouds go. And I think these are amusing plots. This is the emission as a function of temperature of gas at the pressure that we have at the center of a cool core, 10 to the 6.5 in the product NT. If we now jump over here to the cooling time, so that's the time it takes at this emissivity to radiate its thermal energy, then this cold branch down here around 10K actually cools off in about 30 years. So if you have a cool cloud and you don't do anything to it, it's just going to go across to even lower temperatures until you can't see it. It's not emitting anything, and at that point you can't see it. So it introduces the possibility, and I know such things have been thought of long in the past, but how cold do clouds go? Is it possible to make them invisible? And I'm just throwing it out there. I'm not going to say there is a lot of such gas. I'm just saying it's possible that there's more gas around than we think there is. And what we could do with is a nearby example that we can study in more detail. And there is a nearby example. I've already said that the Crab Nebula has optical emission which looks similar to that of cool core clusters. It turns out that the pressure in this region is 10 to the 6.5 as well. And there are cold knots in the Crab Nebula. And these are, this is knot 1, and you can see it's, this is in continuum. You can see that there's some sort of absorption going on. That's O3 emission and so forth. And there's something like 50 or more knots that have been mapped here. The molecular emission from them was first seen by James Graham back in around 1990, and nobody looked again until we looked. That's with Ed Lowe and Jack Baldwin and others looked at these knots and so forth back using a telescope looking at molecular hydrogen. And these knots are molecular. And then just a few years ago with Al Wooden, we applied to look with ALMA. And we were really surprised by how bright these knots are in CO and other molecules. So the cause of these knots are molecular. And some of the knots have also got dust in, a lot of dust. And whether you can see the dust depends upon whether they're on this side of the nebula or on the other side, because you need to have them in front of this, the blue continuum, before you can see the signs of the dust. And this means that dust is forming quickly. The dust there presumably has formed in the supernova remnant and must have formed in the last 1,000 years. And it's also saying that even if you take gas that was dust-free, hot gas, and let it cool down, it's suggesting that it too can end up forming dust. Let's now return to the bubble shocks. These bubble shocks, which I've shown you before, they appear isothermal. They're seen in several clusters, not all clusters. In fact, I think because they're not seen in all clusters is because they appear isothermal. They look like they may be due to the destruction and mixing of cold clouds, and they provide limits on the cold gas and are part of AGN feedback. Let me just show you what I'm talking about. This is from the Chandra image of Perseus I showed you earlier. That is the nucleus of NGC 1275. And this is the bubble. This is the northern inner bubble. And around it is this large shock where the gas is being pushed outwards. And if you take a profile across here, then the density, this is the density here, has a drop as you go outwards. It drops abruptly at the edge of the shock, and it drops by 30% or so. And you expect, if it's an adiabatic shock, to see a ½ kV jump in temperature. And the green is the sort of simple temperature you get from looking at the spectra. And if you try and deproject it, you get the black crosses, but there's no sign of any abrupt jump just there. So it looks to me as though the temperature here has not responded to the high gas pressure jump. And one thing that's then clear is if you look at the edge of this, it coincides with where the filaments end. These are the northern filaments, and you can see they all stop at some point, and that edge coincides with the northern rim of the shock. And I think what's happening is the shock is actually just swallowing up the gas and mixing it in, and that may be why we don't see the temperature jump. Also, when you look at the H alpha around here, it looks like it's got an old-fashioned television aerial sticking out the side here, and that coincides with the shock on this side. And down here, I've already shown you this enormous stretchy filament, which goes tangential rather than radial, and it's actually several kiloparsecs long, maybe 5 kiloparsecs either side, and that's there on the shock there. These ones resemble to me something known as the Witch's Broom Nebula. This is an edge, this is the edge of the Cygnus loop, a supernova remnant, and it's where it's overtaken, the shock's overtaken a gas cloud, and it produces structures that look like this. And I think that's what's happened here, is the existing gas clouds have been actually overcome by the shock moving out. We can't see them all the way around, but I'm suggesting there are clouds which are too small to be visible, many of them out here, which are being overtaken by the shock. So something is, these are just diagnostics of the environment of the cold core in the Perseus cluster. Now, what's the future? Trying to finish now. This is going just back a few years to Hitomi, which had a microcalorimeter on, and it lasted for 6 weeks. Japanese-US satellite, 2016. In its aperture, shown by this array of detectors, shown by this diamond thing, we were able to make very accurate spectra, X-ray spectra of the core of the Perseus cluster. And here's the ion line, and we were able, from the width of the line, to work out that the turbulent velocity in the center of the cluster was about 100 kilometers per second. Then, unfortunately, the satellite was lost. It's going to be resurrected next year as a new satellite called Prism. And that's likely to see much more, even just looking with the same detector essentially at the Perseus cluster, because the picture I've just shown you, the spectrum I've just shown you, was taken with the gate valve closed. The detector is held at 65 millikelvin. That's because it essentially detects X-rays by measuring and measures their energy, the energy of the incoming photons by measuring the change in energy of a small bit of matter that is the detector. And it has to be very cold in order to do that. And it's inside a dewar, and the X-ray beam comes down into the dewar through this hole. And initially at launch, they have a gate valve which keeps everything out. So you can have atmospheric pressure out here before launch, of course. And then a few weeks after launch, they flip it open. You can see that's the device that's going to open it. But the spectrum I'm showing you was taken before the gate valve was open. In fact, the gate valve was never opened with Hitomi, and it's got a steel grid on it, which actually reduces the aperture by a half. And then it's got a large piece of beryllium in there, which is an X-ray absorber, and that's why it turns over like that. So when it's open, you'll be able to see this spectrum all the way down here, and below it can go down to half a keV, and we'll be able to get wonderful spectra of the cool core clusters with CRISM. And I'm looking forward to that. So this is CRISM, what it will eventually look like. And then, of course, later on in the 30s, we're looking forward to Athena. And I think everybody in Munich must know a lot about Athena, which is going to have X-ray microcalorimeters on. So it's actually going to be doing the Hitomi class spectra only on a much better angular resolution. And that will be the ultimate for doing the kind of analysis I've been talking about. I just want to put in a brief advert before I close, and that is the Decadal, the 2020 Decadal in the US, has recommended that there be an X-ray or a far infrared probe class mission, which is a sort of $1.5 billion mission, and one that's been working. The proposals are due next year, and one I'm somewhat involved in is this one called Axis, which is going to have, it's from Goddard, it's going to have arc-second imaging, so rather like Chandra, only it's going to have 10 times the collecting area of Chandra, so it's going to be something like this. So it will be wonderful for taking images across the centers of cool core clusters. And just to flag that the reason we can't do a lot with the soft X-rays in core clusters at the moment is because Chandra has got a contaminant on the optical blocking filter, which is making its response drop off like this. At launch, it was more like that. But nevertheless, you can do interesting work on core clusters, of course, above about a keV. So it's still got its response up there. But the kind of thing I'm talking about with regard to the gas cooling below below 1 or half a keV is best, is very compromised here. So in summary, cooling flows may cool below 10 million K, hidden by intrinsic absorption. I hope I've made that point. It's something that's been thought about for several decades, but the last 2 decades, people have, including myself, have tended to sort of not go there. The mass cooling rates could be several times the unabsorbed estimates, and most of the absorbed energy emerges in the far infrared. It could be that there are a lot of colder clouds out there. This is very much a speculation, and I'm interested in your thoughts on that. And it all has implications for star formation. That there's lots of cold gas in these objects. Much of it is probably 1 billion years old or more, or older, which is not forming stars. Why is it not forming stars? Why does sometimes it form stars? The total gas is controlled by bubble shocks and outflows. So cold gas is accumulating in the centers of these things, but it's then being dragged outwards, and it's also being shocked and at the same time mixed in. The inner few kiloparsecs of cool cores are very complex and multi-phase, and they're crying out for deeper observations at all wavelengths, and radio through X-ray. And I'll be really interested when JWST makes its first observations of the center of a Cool cluster. And for those of you who do numerical simulations, I will say the large range of relative densities and sizes, the densities, if it goes from below 10K up to 10 to the 7K, is over 1 million. And the sizes, which may go from sub-parsec up to 100 kiloparsecs, that will challenge your numerical simulations. And I'll end there. Thank you.